The story begins in the 1940s, when a young Richard Hamming was working for Bell Labs, and some of his work involved using a very big, expensive punch card computer that he had only limited access to. And the programs he kept putting through it kept failing, because every now and then a bit would get misread. Frustration being the crucible of invention, he got so fed up that he invented the world's first error correction code. Let's use an example that's simple, but not too simple. A block of 16 bits. We'll number the positions of these bits from 0 up to 15. The actual data that we want to store is only going to make up 12 of these bits, while 4 of the positions are going to be reserved as a kind of redundancy. The word redundant here doesn't simply mean copy. After all, those 4 bits don't give us enough room to blindly copy the data. Instead, they'll need to be a much more nuanced and clever kind of redundancy, not adding any new information, but adding resilience. But before we can dive in, we need to talk about a related idea which was fresh on Hamming's mind in the time of his discovery. A method which lets you detect any single-bit errors, but not to correct them, known in the business as a parity check. For a parity check, we separate out only one single bit that the sender is responsible for tuning, and the rest are free to carry a message. The only job of this special bit is to make sure that the total number of ones in the message is an even number. So for example, right now that total number of ones is 7, that's odd, so the sender needs to flip that special bit to be a 1, making the count even. But if the block had already started off with an even number of ones, then this special bit would have been kept at a 0. This is pretty simple, deceptively simple, but it's an incredibly elegant way to distill the idea of change anywhere in a message to be reflected in a single bit of information. Notice, if any bit of this message gets flipped, either from 0 to 1 or 1 to 0, it changes the total count of ones from being even to being odd. So if you're the receiver, you look at this message and you see an odd number of ones, you can know for sure that some error has occurred, even though you might have no idea where it was. As Hamming was searching for a way to identify where an error happened, not just that it happened, his key insight was that if you apply some parity checks not to the full message, but to certain carefully selected subsets, you can ask a more refined series of questions that pin down the location of any single bit error.